Hey everyone, welcome and thank you for joining us. Thank you for choosing to spend your time with us today. Today's webinar will cover wolfHSM, designed for automotive hardware security modules, presented by wolfSSL Software Engineer Bill Phipps. My name is Cameron, and I will be moderating the webinar. All attendees will be in listen mode only. If you have any questions, please use the Q&A box. After the presentation, Bill will answer any of your questions. As always, our webinars will be recorded and made available on our YouTube channel, as well as a PDF version of the slides. If you would like to stay updated from the latest on wolfSSL, follow us on Twitter, connect with us on LinkedIn, and subscribe to us on the YouTube channel. Also, feel free to email us at facts@wolfSSL.com if you have any additional questions that come up. Before we dive into the presentation, I'd like to give a brief overview of wolfSSL. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we're extremely proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-178 support, FIPS certification, and FIPS ready offering. MQTT up to the V5 specification, SSH2 or V2, TPM 2.0, a secure bootloader known as wolfboot, as well as Java wrappers and JSSE support, and a commercial support for curl. And of course, wolfHSM. And all of these offerings are going to be accompanied by thorough maintenance and support plans all the way up to the 24/7 level. And we do offer full service consulting. And now I'd like to turn over to Bill to talk about wolfHSM, designed for automotive security modules.
Thanks, Cameron. Again, my name is Bill Phipps. I'm a software engineer with Wolf, and I've been here for just over a year. So we're going to talk through some of the wolfHSM design, how we're a little different than other HSM solutions today. Do a short demo of two different ports that we've got, and kind of walk through a typical path of doing a porting to a specific new kind of hardware, and then we'll walk through some of the future directions. So right off the bat, a lot of people are curious what exactly an HSM is. From our perspective, and we view this from a logical perspective, an HSM gives us an execution context typically on a separate hardware core that has access to low-level platform-specific security features and typically hardware crypto acceleration. The important aspect of an HSM core is the fact that from a physical attack perspective, it's isolated, it's separate, and it has some additional security provided within it to make it your job easier, and you can focus on putting whatever applications that you want to put together and not have as much of a concern about the security aspects from that. HSM core typically will service multiple application cores where your main application will run, and these application cores in an HSM solution would make callbacks to or requests to an HSM core that would execute the job. What you'll find as you take a look at HSM offerings that are out there, you end up with a toolbox. It is an opportunity, a hardware opportunity to put things together, but it is a lot of effort to put together a full-blown solution. So from this logical perspective, HSM core is a separate execution context, and we've got application cores that have some library aspect to be able to talk to the HSM core to do security work. How does this contrast with other secure element solutions? So we kind of see this between where a TPM, a trusted platform module, would sit, and a trust zone or fully virtualized software-based solution with some hardware support. HSM kind of does the best of both worlds, if you will. And that's why normally they only exist on higher end chips. From a TPM perspective, our simple categories here is a TPM is non-user programmable, whereas an HSM and a trust zone solution or a virtualized solution is fully programmable. This means that you can't modify the code in a TPM, which is a good thing and a bad thing. Tightly coupled, the TPM is typically not tightly coupled, meaning it shares the same memory buses, it's sitting in the same memory space, and potentially has DMA access. TPM is designed to be distinct from the CPU, but this also introduces another attack path. Both an HSM and a trust zone solution, those are on a shared bus within the same system typically. And typically the HSMs have access to address controls on top of those shared buses. TPM certainly provides hardware crypto. Most HSMs provide some hardware cryptography. And depending on what you need to do, you might be limited in either the sizes or the algorithms that are offered in hardware on the HSM. And a trust zone solution doesn't do any real hardware crypto. It's all software based. From a physical protection perspective, both the TPM and the HSM provide physical protections, and that may be also something that you can tie callbacks to, so that if you notice a tamper detect, you might be able to take an action based on that. Trust zone really doesn't have that. They do have some abilities to handle exceptions and say, hey, there was a violation in an address space, but aside from that, it's a partial solution. It doesn't really provide any physical protections. They're all logical protections. TPM do provide non-volatile storage, as well as most HSMs have separable parts of flash or entirely different chips that are used to provide that protection. A trust zone solution does not. You're absolutely sharing the same non-volatile storage as the main application cores. And again, likewise, from a tamper response, TPMs can do certain things. HSMs, you typically are given the entire bag of options to deal with. And then again, trust zone virtualized solutions, there really isn't any tamper response aside from triggering like a non-maskable interrupt. So we see the HSM from a secure element solution as kind of fitting between these two pieces. From our perspective, looking at where what an automotive HSM is taking a look at some of the functional requirements, the HSM's got to be involved with a secure boot of the overall ECU. It's got to make sure that what is about to be running or is already running is what is expected to be there, and it's intact, and from a compile time perspective is authenticated. Also need to make sure that the HSM is involved in any updates that were applied after it left the factory to ensure things like rollback prevention or the authentication of an update package. These are all cryptographic features that an HSM will need to be involved with. Also, there needs to be some concept of being able to protect critical pieces of either calibration or configuration data to ensure that a user can't gain access to it or unlock features they're not supposed to have. These are, again, HSM can be involved in that either by securely storing data for the user or providing key storage that then the user can decrypt only certain portions of that. Obviously, providing cryptographic operations. These are, again, key storages, private keys, making sure that keys are used in the right way. And these would be used for encryptions and hashes and signatures and other types of security solutions from there. Normally, the HSM has to be aware of the debugging or testing interfaces and make sure those are disabled in production units, and then really support the overall product lifecycle, ensuring that if there's a failure analysis, that the HSM can understand this isn't a failure analysis lifecycle and certain features need to be fully disabled, whereas others we need to look at what happened to the chip. Those features can be enabled, but protecting anything that was critical at the time of. At the end of the day, also the HSM solution, both on the client side and the HSM core side, need to make sure they can meet real-time and safety critical requirements. So fundamentally, the automotive industry has needs that are kind of both in the real-time safety side of the house and security, as well as cryptographic. And this is really where the HSM hardware solution can be married up with a good software solution. So when we take a look at an HSM solution, we really split it into two different areas. One is an HSM secure area where we believe that we have physically protected components that we can work with. Really starting with the HSM core, again, this is typically either a slower or a different model of the main application core that has access to any custom controls that the platform provides. These might be to enable or disable, let's say, things like JTAG or peripherals that shouldn't be enabled that are on the chip by itself. It may be crypto acceleration hardware, and so the core may be the only one who can access certain parts of the crypto backend. You'll definitely have a local chunk of RAM that you can execute out of securely and distinct from the rest of the application, so you can execute without being interrupted. And likewise, most HSMs provide a non-volatile memory area, usually some sort of flash that has some specific use cases against it. From the non-secure area, we've got, again, a multi-core solution that's tied into some shared piece of RAM that both the HSM can talk to. This might be registers as well, and the cores can talk to, as well as there's typically a shared non-volatile memory area that the HSM can say read and write to be able to do measurements of core applications. But the cores normally would be in charge of updating and writing to that NVM. Most of the core layouts have separable local RAMs, and they each can run their own individual application, if you will. So we color this a little bit differently. Where do we exist from an HSM product? Well, we certainly are providing an HSM client library that your user app could then call into, which would then expose cryptography as well as communications from the core through the communication buffers to the HSM core, who can then service that request. From the HSM core perspective, we typically are providing a straightforward bootloader that allows the core to come up from bare metal and then execute an HSM server loop, which is simply sitting there waiting for requests to come in from the client. There's another step through the boot sequence where the core is able to perform boot time measurements either prior to or while these cores are booting. So we can understand and measure the state of the non-volatile memory and potentially some of the shared registers while the system's running, and then provide that information back to support a measured boot sequence. So logically, this is how we see the system laid out, and you'll see that when we lay this down, at least for the Tricore, this model works out pretty well. So at the end of the day, we've got an HSM client software component that's executing typically in local RAM for each of the cores, and we've got an HSM server component which executes locally through the HSM core, and then communication buffers between them. Again, typically segmented shared RAM that's been allocated for that at compile time. We have been doing crypto for automotive for a long time. A lot of our customers have embedded our solutions, either Wolf Crypto, wolfSSL, or even our Wolf Boot product into their automotive products. And so we are familiar with this space, and we're familiar with having to make things tight, small, and meet requirements. So I did want to point out, we do have a lot of experience in this area before we talk about the overall, bring it all together as an overall solution. So our wolfSSL and wolfCrypt is our base software crypto engine that does support hardware offload. So as you're writing your code, you can write it once, and whether it's executed in software or in hardware, you can let that be figured out either at runtime or at compile time, but your code doesn't necessarily have to change. We got a stable API that has been around for many, many years. And so that's kind of our starting entry point for our cryptography solutions. Wolf Boot is a secure bootloader, which has a lot of overlap with the way wolfHSM has to run, as well as the HSM server tasks that we see. Again, this is designed to offer a managed boot sequence, which can support an encrypted a measured or an encrypted application load. There's actually overlap and code that we share between Wolf Boot and wolfHSM for the initial bootstrap and the image management. We do expect we will end up merging some of these products together, but for now they're separate and managed independently. So we're very familiar with how to boot up lots of different platforms and do those in the secure fashion to make sure that we can handle fail-safe updates and things like that. wolfSSL also has TPM and crypto callback interfaces. These are designed to extend the way Wolf Crypto runs to be able to access things like TPMs or third-party cryptography libraries, typically for hardware acceleration or things that are very custom to that. Again, this abstraction layer is how wolfHSM actually works. It acts as an abstraction layer to wolfCrypt, but we do have full support for TPM as a client access library. Wolf PKCS11. This is a PKCS11 provider interface that allows the wolfCrypt engine to act as a PKCS11 responder. We also are bringing the PKCS11 as an interface to wolfHSM, which means if you happen to use the PKCS11 interface to reach to your secure element, we will understand that natively and be able to expose any of the wolfHSM features through a PKCS11 interface. One of the other advantages we also have by providing a complete software crypto is that we can also offer other types of cryptography solutions and suites where we actively support post-quantum development, and we have multiple post-quantum algorithms implemented. This allows you as a customer to buy an HSM today, implement us as the software backend, and then expand in a software implementation perspective what that HSM can do. This allows us to place post-quantum ARIA or the Shengmi cipher suites into your hardware, execute them on the software side of the house, and then you still have that ability to get you some crypto agility and to be able to update as these algorithms come out. We've also found that some of the post-quantum, specifically in the signature side, those algorithms are smaller code, generate smaller signatures, and execute faster than some of the traditional non-post-quantum. So there's actually some performance reasons why post-quantum should be considered, specifically in the automotive industry. Overall, our goal for wolfHSM, really number one, was to make sure that we had open source software that was available for both the server and the client library. The HSM server code normally from vendors is locked down, and it's provided as a binary or a precompiled solution. We think this is missing a huge opportunity in HSM server side. And so one of the major goals was to ensure that your code could execute both on the client side as well as the server side to provide a build environment and a framework to add custom functionality that can execute in that HSM context. It also allows you to get rid of functions that you don't need. If, let's say, you're not using a DSA, there's no reason that your HSM server should have DSA. That should get ripped out of there. So this allows you to customize your HSM server to only have those features that you need, as well as extend that to add in your own functional components that are in there that should be executing in a secure context. This also allows us to fill in, let's say you got an HSM that has limited hardware crypto. By adding the rest of these algorithms in and software, it gets you in a position that you can stay up to date with whatever the requirements happen to be, or fill in those missing crypto functions. We found, even, I'll pick on the Tricore, for instance, sure, it can do some of the public key computations, but the key sizes are not sufficient for even something like RSA. It's totally fine for an elliptic curve, but they simply aren't large enough to handle RSA functions. So this allows us in software to implement those missing RSA features and still have it execute in the HSM context. We also wanted to make sure that we maintained an API that was similar between our software and hardware operations, as well as HSM versus client-based operations. So we've extended the wolfCrypt API with a couple of helper functions, but the bulk of the wolfCrypt API remains intact. And if you already have code that's written for wolfCrypt, it should lay on top of wolfHSM almost with no modifications. We wanted to ensure that we could support asynchronous operation. This allows us to limit time of certain operations from running so that you, as a real-time system, you have an expectation of how long some of these functions run. Everything we do is a request response. And so you're allowed to issue a request, go back and do some other work, and then check to see if the response is available from a client-side perspective. We're famous for how small we can build in our usage of static memory and our minimal requirements on a system library. And even if you don't have, let's say, a nanolib or a newlib type of solution that's available in your build environment, we can supply suitable small functions that do the exact same pieces. So we can do completely bare metal solution with no operating system, nor even C runtime library required. Again, tailoring to remove features that you don't need. This is our claim to fame in terms of the configurability of wolfCrypt and our wolfSSL products. And one of the features at the bottom is we do provide a POSIX simulator that lets you test the system before you even get the hardware. And what I'll be showing you today is a set of example programs that run not only on our host systems, but then, in essence, unmodified source code, we drop it off and execute it on an embedded target. The only modifications we make is switching out the configuration for the platform-specific communications. Everything else, the code stays exactly the same. So moving back on, we've split HSM into two basic functional components. One is the client library, which every client library starts off with wolfCrypt, and we port this specifically to the application core architecture that you're running, which, again, may be different than your HSM core. So this allows you to configure wolfCrypt optimized for that specific core. And actually, the Tricore is a great example. The HSM core is a Cortex M3, and the Aurix Tricore has multiple Tricore nodes. This allows us to enable certain assembly offload features that we've got on the HSM core, and then we can use other types of optimization for the Tricore application cores. Again, this allows you to configure it in two different ways. In fact, one of the demos I have, we have two different versions of wolfCrypt running. configured in two different fashions. This allows us to limit the functionality on the client and add certain functionality to the server, so that you can kind of fill in those blanks and kind of go from there. HSM client library, we perform any of the crypto offload from the HSMs via our standard crypto callback mechanic. So this is a well-worn path. So we know that the way that we're going to be invoked is working just fine. And it gives you the ability to take existing code simply by modifying the device ID that you're pointing to and have it offload that to the HSM server. The client library also provides all of additional key management and non-volatile memory management functions that are in addition to wolfCrypt. And again, we do understand protocols like SHE and how to act as an AUTOSAR crypto driver, as well as PKCS11 if that was necessary. From the server perspective, we do start with a bare metal startup that's based on our wolf boot starting up sequence. This also grants us NVM access to the HSM specific flash. We also port wolfCrypt to that, the core architecture. We then implement any of the hardware crypto that we have. We implement it as a local from the server's perspective, crypto callback feature. We then bring in any of the additional security controls that the certain platform has, and we can tie those into custom wolfHSM callback functions so that the client can then trigger those features. And the example I have, we enable and disable debug interfaces and the Ethernet interface on the Tricore using these features. We do have an image manager that can help support that chain of trust. If you have a root of trust that you want to leave in the HSM, but then prove that as the client's boot, they are meeting certain measurements. Again, the image manager helps you in the HSM server, as well as we do understand how to act as in this case, a SHE server, so it can maintain the state that would simulate what a SHE server should be doing. So moving on from a picture perspective, overall, you start off with your base application. You link in the Wolf client API, which again, this is fully configurable. So you can specify how you want wolfCrypt and how the client's going to be talking. You'll or you'll communicate with the server via a port specific transport. And again, we provide these for the Tricore and the other ports that we've got. But if you get a new hardware platform, it's just a handful of communication functions that have to be implemented to support porting. The wolfHSM server application, again, we provide a baseline for that for these platforms that basically just boots up, mounts the NVM, verifies the NVM is in a state it understands, sets up a key manager so they can handle incoming messages that need key support. And there's an example of that coming in, as well as it sets up wolfCrypt and starts up the hardware crypto engine. After that, it jumps into a loop and simply waits for incoming requests. So fundamentally, you're ending up with two basic software modules. One's a software library, and the second is a full executable. Breaking this down a little bit deeper from a client library perspective, there's a fixed API that exposes the additional wolfHSM client functions, as well as a couple of helper functions to help with wolfCrypt. The black color is set. This is an unmodified version of wolfCrypt. We simply grab master, and from our perspective, using GitHub, configure that, and then link it off from there. This gives the entire software crypto library that wolfCrypt provides to be available locally to the client. And then anything that the client chooses to pass to the HSM server would go into our HSM crypto callback, which then this basically takes that same request, routes it through these port-specific communication buffers for the server to process that. Also on the client side, it exposes an NVM manager, which routes all calls to the HSM's client or to the HSM's NVM, as well as key management, which again routes it to the HSM. We can also support keys by identifier in a local store as well. From a server perspective, the base server boots, which is again a bare metal boot to get from the reset vector and jump in. It performs any image manager functions that you have, which might include measuring the HSM server code itself, as well as any of the client code that may be out there to generate and store those measurements. It may also then choose not to boot the clients or release them from reset if it detects that there's been a problem. So there's some options of how you want to handle those types of things. And then it jumps into a loop to handle those requests. From the server API perspective, what you'd be coding against if you wanted to place additional code into the server, you'd have a full server API. You still have your full wolfCrypt available to you, which again may be configured differently than the client. You've got access to a key manager and a non-volatile memory manager. And again, normally our NVM manager is pointed to use the HSM specific flash, but you can also use main flash, which would be shared with the clients if you needed to store some additional objects out there and you don't have any security concerns with those objects. As a key manager perspective, we do provide a local set of RAM keys that the user can leverage, as well as it can redirect key requests to go to the hardware crypto. Some of the hardware crypto provides ROM-based keys that are only existing in the hardware crypto, and this interface allows you to gain access to those. In addition to the Wolf Crypt software crypto, we also have typically we'll port the hardware crypto interfaces as a crypto callback. So from the server perspective, you can invoke functions to be executed on the hardware that's local to you, or you can have those same functions execute in software or vice versa, however it happens to be. Typically, there's more platform-specific things in the server executable. So you do have to handle the COM buffers, the other side of the communications that are coming in from the client, interrupt handling, as well as typically there's hardware interfaces and IO controls that you need to set up. So those things are all port specific on how you want your server to be involved with the client. So fundamentally, logically, that's how the whole system works together. I did want to again point out that Wolf Crypt is actually the bottom end for a lot of different crypto drivers that are in the industry already. And again, that works well. So we understand the automotive requirements. We're really high on all of the modern crypto and making sure that we're ahead of the standards requests to make and help our customers be ahead of the curve. wolfHSM kind of follows in that. We continue asynchronous and abstracted layers. So this lines up well with how AUTOSAR wants to view us and leverage some of our features. So even if you have been using us, Wolf Crypt by itself in the crypto driver layer, we do believe this would be a quick fix for you to swap out and put wolfHSM in there and then offload some of those features to hardware HSMs, which is becoming more and more of a requirement. The other thing to point out is that our server solution is user extensible. So if there is a set of custom functions you want to do, you can simply extend the server, recompile it, and roll it in, and then access it that way. So that type of being able to extend what is happening in a server is I think important, and I think it lines up well with how AUTOSAR cryptos offer some vendor supplied or some vendor function that are custom to those guys. I'm going to flip through a couple more of these real quick. You'll get the full slide deck, but fundamentally, hopefully that's the logical layout. I did want to make sure we left plenty of time to walk through some of these examples and how we do porting. So I'm going to walk through just a couple of these from I'm going to give an example of how the key management works from the client's perspective. So on the left-hand side, this is how we would normally set up an AES operation using Wolf Crypt. Yeah, you'd instantiate an AES context. You would then set the key. In this case, you've got the bytes that represent that key local. You'd associate that key and the initialization value with that AES context. In this case, we're doing a CBC encrypt. You can encrypt some cipher and get you can encrypt a plain text and get a cipher out, and then you'd free the context. From a wolfHSM client perspective, the black code stays exactly the same. The only difference now is instead of having the key material, we're going to say, hey, there's a predefined key on the server that I'm calling C3 key 1. This is an identity or an ID value that has been preloaded in there. And so the server knows how to interpret that value. The same AES init call, except now we say, hey, for this context, I'm going to route all of my functions to the wolfHSM device instead of local software implementation. One additional function call says, hey, as a wolfHSM client, I want you to associate in this context this specific key ID. And previously, you were setting the key as just a raw sequence of bytes. We then set the initialization value of that context, the exact same call we did previously, and then you invoke the encrypt and free. So to be able to leverage a predefined key on the HSM server and then route the request to do this AES CBC call, you see the number of lines of code changed is very minimal. Number one, to route the call was to set the dev ID. And number two, to set which key to use is simply another wolfHSM client call. So again, this is how we wanted to see it happen, is that extending functions to work on the HSM should be as simple as this. This is the same type of example, but instead we're going to load the key that we've got locally into the server, and then we're going to ask the server to use that key. And so same type of setup that we've got a key storage. We're going to start off with a key that we say we know it's an invalid key ID, which is a clue to the server he needs to allocate a new unique ID for us to use. We set up the context the exact same way, routing all the calls to the HSM device. This wolfHSM client key cache request says, hey, please cache this key that I'm about to give you, and then tell me what key ID you allocated for me to use for that. And again, this key cache simply puts it into a RAM state, so that way the server will hold on to it with my context, and I can use that key from that point forward. After this, it's set our key ID. I go back to the exact same function call to say, hey, now associate my AES context with that key ID that was just allocated for me. Set the IV, do the encryption. And again, this AES CBC encrypt, that's just a request for the server to do the work with the data that I'm passing. And at the end of the time, when I'm done with using that key, I add one more function call that says, hey, evict that key from my cache. I could have also asked the HSM to store that key in NVM. And then from that point forward, next time I boot, I wouldn't have to do a key cache. I could simply say, hey, use this key ID now that I know which key ID was allocated for it. So again, from a key management perspective, it gives you a great opportunity to place things either temporarily in RAM and use them and have the HSM do the work for you. Or in this case, you can do it and then forget it. Again, that's the idea of being able to add some straightforward key management to our WolfCrypt solutions. I'm going to walk through a couple of these pieces on NVM. NVM is a big deal in the HSM. It's important that writes to the NVM are verified to be correct, and that at any moment you can recover any data that may have been partially written to there. So with everything that we write to the NVM section, we solve this by simply splitting the NVM into two parts, one which is an active partition and a second which is an inactive partition. We basically linearly write to the active partition until it's full, or until the user asks us to replace it. And then we simply copy all of those things that haven't been erased from the active partition to the inactive partition, and then start to use the inactive partition. We keep track of where we are in each of the writes, not with some global log, but with simple flags that are associated with each object that we're going to write as we're going to write them. So from a recoverability perspective, you always have at least one copy of all your data in one of those partitions. If you're halfway through copying it, and let's say you lost power, when the system came back up, it would notice, oh, I've got two copies, but the second copy is incomplete. I'll simply use the first copy and we'll recover from there. So at any moment, things are recoverable, and we properly handle partially written objects from that perspective. So fundamentally, we start up with a fixed layout, a certain number of directory entries, and then some free entries that are beneath that. The directory simply holds the metadata and offsets for the data that goes along with those entries. And again, there's a fixed number of entries in the directory to use, and that's something that can be set at compile time. The data is, again, just a stack of data that is appended to until it's full, and then you simply copy everything over from there. Again, on startup, we attempt to read the directory and reconstruct each of the objects to verify which object is the valid object, and then go from there. So the sequence of events for each object that we have, I'll pick on an object entry, for instance. It has 3 additional flags that are written atomically. When I go to create a new object, I'll write this epoch flag first, which has a counter value in it as well. Then I will write the metadata for the object. And again, objects include some space, 24 bytes of a label, as well as additional ID values that make sure that we can describe the data easily enough. And oftentimes you can actually store the data you want to store actually in the metadata label itself. But this lines up with the PKCS11 style metadata object. So anywho, the first time you write the epoch, then you write the actual metadata objects, then you write the starting offset to the data. You can then go write all the data, and then you'd last write the size of the data that you wrote. So at any moment, if one of these is not filled out correctly, you can understand on recovery what didn't actually happen, and then recover from there. So all of the NVM objects that we have that we expose are stored in this way, which means they're recoverable and safe to move forward, and we can understand the status of each. I kind of just walk through sequence these next couple slides. But from an API perspective, this now allows us to perform, let's say, to write a piece of data and then retrieve that data back. And this is arbitrary data. So as long as you've got space, the NVM will store it for you. So this goes beyond what PKCS11 does, which only stores key material. You can store, in this case, I'm storing a string that says, this is my data, and I've identified it with this is my label, and they have a unique identifier for it. So to do this, you would initialize your client. You'd set up this metadata, which again is just a struct that has this information. We'd add this object in, which is the metadata and the size of the data that we're passing. And then after we've invoked this function, the HSM will commit this data to the NVM and say, yep, everything's good. This also allows us, after the fact, if you happen to write the exact same object with an updated data, it won't necessarily overwrite the old data, but it adds a new version of that object into the NVM and then mark the previous set of data as recoverable. And so this allows you to update data as you go, and then every once in a while do a recovery, which kind of cleans everything out and goes from there. And at any moment, you can lose power. And if you didn't fully complete this object right, then when it comes back up, it'll detect it and it'll say, it'll just simply skip that and mark that as a recoverable space and then move forward. To retrieve that data, again, initialize this. In this case, we knew what our ID value was. We get the metadata and place that into this metadata structure, which would then give us this my label, if this is what we're looking for. And then we can just use a read function to say, hey, read the data from that specific ID into my buffer, and boom, we've got it. So that's, again, NVM management and objects. Those are fronted on top of the flash layer. So this makes it very simple for you to store, let's say, calibration data, and this data is being stored in the HSM server itself. There's listing and destroying functions as well. So let me work through how we normally do porting and how we do testing. So the HSM wolfHSM library is designed so that you can take the exact same code that you've written with a different configuration, recompile that, and place that onto your embedded target. So we almost always start on the development host using our POSIX port, where we would start off with some sort of either demo or example or unit test application, which would compile against a compiled version of the client library. We then also build a server application that can then answer that. So if, let's say, you're using TCP as a transport, you'd fire up the server app on a certain port, and you would have configured your test app to connect to that port and then issue the requests. The joy here is that as you write those HSM and wolfCrypt functions to do whatever test you'd like to perform, you can take that exact same code, swap out the configuration, recompile, and run that onto your target. But this time, instead of using some POSIX-based transport, TCP, shared memory, threads, whatever it happened to be, you would then switch over the configuration to use a hardware-specific version. And I'll give you a couple of examples as we go through this. But this allows you, without hardware, to get your code working in the way you want it to work on your host desktop, and then simply bring that test into whatever the build environment is for your embedded target, and then port that and go from there. So you'll see the examples we give here are literally our unit tests that we use to verify wolfHSM or wolfCrypt in this case as well are working correctly, and they generate the same text output as how we normally see it. But it's not it's the only thing we've swapped out is the configuration of how to talk to the server. And that's a big advantage. It really does help to improve your ability to troubleshoot what's going on and then make sure that you're working the way you wanted it to work. So we do have a couple of ports that were currently in progress. We did release a version of our Aurix TC3 port, which is I'll be demoing part of that today, and which we do have full crypto offload for everything they offer. And those have been linked back to wolfCrypt functions. So if you're familiar with wolfCrypt functions, those are now ported directly to talk to the hardware. And we've also got an ST SPC58 series, which is a number of PowerPC cores with an HSM core as well. It has a much more limited set of crypto offload that's available. And so that server has a lot of software support to fill in those blanks for that. When you go to do a port, you can start off by having null interfaces to do things like flash memory or the hardware crypto, just to make sure the communications are working. But at the end of the day, you'll need to implement something that works with whatever port you're doing to access the non-volatile memory And again, typically flash-based devices where you've got these types of intrinsics, read, erase, program. Crypto hardware, again, there's key management, there is different types of crypto. So you'll need to map those into our crypto callback functions. And we have examples specifically, this has been done for the Tricore and the SPC already. And then likewise from a platform interface, the boot sequences are typically very custom, especially on the HSMs, to make sure that you're setting up registers correctly on that chip. How to handle controlling the resets, the application cores, and then making sure that any memory mapping limitations are in place. Those typically need to happen prior to releasing the application cores from running. From our perspective, we expect the porting and the configuration files to be selected at compile time. And so this way you can build your objects down, press them into the embedded platform, bring it up, and then make sure everything's working correctly. Just as an example, when we do testing, this is an example of how you would configure, in this case, a flash file simulator using our POSIX backend. So again, all we did is we use a POSIX file to store the flash, but the interface to it isn't read and write. It is read, erase, program, blank check. So it looks just like an actual piece of flash. When we move this exact same code to the hardware, we don't have to replace the upper level functions. We simply replace the bottom end handlers for this flash implementation. So typically what you would do, you'd set up a set of callbacks. This is where we're specifying what functions to call when we want to do specific flash file functions. If it was a different flash, let's say the Tricore, we simply provide the Tricore callback functions there. When we create a context, this is the dynamic state of any of our flash components. And we're starting off blank. You would set up a configuration structure, which then is specific to whichever callback you've selected. And these are the pieces that are necessary for us to configure the flash file callback. And then at the end of the day, you would simply connect from a different configuration, say, hey, I've got an NVM flash device. I wanted to use my POSIX flash file context with this POSIX flash file config. So this is an example of a configuration. When we bring up, in this case, a server, you'd simply point it to this flash config, which then understands which callbacks to use, which context to use from a memory allocation perspective for dynamic state, and then which configuration to use. When we swap out, you simply modify this configuration to point to, let's say, the Tricore callback, the Tricore context, and the Tricore config. The rest of the server code doesn't change. And that's a huge advantage for porting things in. Let me jump in. I'm going to have two demos today. One, which is a wolf crypt and a platform demo that we're running on a Tricore 367. Again, the Tricore 367 has got two Tricore cores. It's got an M3 HSM core. It does have a bunch of hardware crypto offload available to it. This demo sequence is one of the first ones we do when we're doing a port to a new hardware. We bring up both cores and then make sure that from an interrupt perspective, they can talk to each other. So there's a common initialization. We then run our standard wolfCrypt test and wolfCrypt benchmarks on, in this case, the Tricore Core 0 first. We then repeat those exact same tests on ARM, the ARM HSM core. We then go through a sequence of functional tests to prove that we know how to access the hardware on the Tricore features, the hardware features that are there to prove that these things are working correctly. So again, this is a functional test. This is normally how we would start to perform a port. The next demo, I'll walk through the finalized wolfHSM version of this, which then walks through just wolfHSM high-level functions as opposed to these low-level pieces. From logically, you'll see that we've got exactly two cores. We're going to keep the second core in reset, and we're only going to be executing off of core 0. We do have a standard bootloader and HSM server that are loaded into the HSM RAM at startup time, so these guys can communicate through a shared memory buffer. Couple of notes, we did swap out any printfs. So if an HSM wants to print, it'll actually send a message to the Tricore then dumps it at the serial port. So that's how we're getting the ins and outs here. And again, this test is just to prove that we can compute things the right way and then run benchmarking. We did build this using the Dev Studio, using the GCC Tricore. wolfCrypt has our single precision math library built specifically for Tricore and wolfCrypt on the HSM. uses also an SP math library, but we have optimized assembly for a lot of those function calls as well. So this is pointing out we can have two different flavors of wolfcrypt interoperating at the same time. Let me switch over and actually pop that up real quick. So, all right. So what I've got here is the output of those two builds. I'm going to hit the reset button on this guy real quick. And so we'll watch him start up, and I'll walk through pieces of this as well. This is running live. So you see it's actually paused here as it looks like it's paused. It's actually computing a new RSA key. But let me scroll up and I'll show you where this started off with. So at the very beginning, we've got the Tricore coming up. It just spits out a little helper message. It communicates with the HSM to make sure the HSM is enabled, it's on, it's responding, and that's just a quick round trip test. We then jump into our wolfcrypt test. Now, in this case, we've compiled on the Tricore, we've compiled wolfSSL 5.5.0, and so it's walking through doing known answer tests for every type of algorithm that's been configured for that. And just as an example, I'm going to pull this up real quick. This is on my Mac. I'm going to run the exact same test to show that the output that we have, we literally link in and build that. So this is the same exact wolfcrypt test. This is for version 5.7, but for the test I've got here, it's running locally. So you see the exact same output, same exact code. This is when we talk about things being portable, this is exactly what we're talking about, is ensuring that I'm getting answers to known answer tests, and they're working the exact same way. So here's one of those. Let me scroll back down and let it finish. Oh, sorry. So the next part is running a benchmark test, which attempts to, it finished all those tests. The next part is, again, running benchmarks. It goes through each of the algorithms, tries to run it for roughly 1 second. In this case, we're doing 1 kilobyte blocks. And I'll pick on this AES 128 CBC. Again, this is just wolfcrypt running, but this is the unmodified Wolf benchmark program. I'll do the exact same thing on my host real quick, just so you can see what that looks like as it runs. Again, targeting for roughly a 1 second. So it's the exact same output, same type of things we're looking for. I'll let that run in the background. The performance numbers don't really matter, but these are reasonable performance numbers with a 300 megahertz 32-bit core that the Tricores are. So after it finishes all of those benchmarks, it now switches, and it's now asking the HSM, the ARM core, to perform these tests. Now you'll notice that the ARM core, I've built this with a 5.6.3, again, showing we can use different versions of wolfSSL. It's running through doing the exact same tests the way it's configured to do it. And now it's running through benchmarks. And you'll see that the ARM core on the Aurix is only 100 megahertz, so its performance is significantly less, and it has a lot different caching performance. It's a lot less than what the Tricore was at 300 megahertz. And so the nice thing here is as we go to enable hardware offload, you'll see that performance jumps back up again to show that, yes, that when the ARM is triggering the hardware to do the work, you'll get additional performance out of it. Again, the joy here is that you compile it once, or you write the code once, and you simply compile and deploy differently to end up with those different operations. Let me switch back to, while it's finishing off, there you go, just finished all those off. So I wanted to point out a couple other pieces that are there. On the server, I've configured ECC to be only the prime 3D4 R1 curve. So this is a good example of how we can change the configuration. On the client, though, on the Tricore, you'll see we only have prime 256 enabled. So this allows you to only place the algorithms that you want in either the client or the server. That configurability is very important for us. Let me just finish off the last piece here of this simple wolfcrypt test. So here we run a slightly different AES CBC encrypt test. This is hardware offloaded. Again, this is a smaller test. This is using 256 byte messages instead of 1024. But you'll see the performance when the HSM core is running that with offloaded, it's getting about 3.4 megabytes per second, which is similar to what we saw the Tricore pulling off. Again, slightly different configuration, but it does prove that when the Tricore is asking the HSM core to do the work, it can successfully hardware offload. Let me switch gears and get back into our thing here. So from what you just saw, these things were live run, so you know, slightly different performance numbers each time, but I kind of just pointing out, you know, how we've got different configurations that are available to us. And let me keep going on. This is the HSM running that same test that you just saw running. And again, we pointed out it's slow by itself, running in software. Prime 384. Here where we were testing the hardware random number generator and then use that to seed our pseudo random number generator, generating an ECC key pair. And you can see this will be different every time, storing it to memory so we can see it. And then again, you can see the performance of the crypto tests there. So let me switch to the second demo. Now that last one was a kind of a technology demo, what we would do to port. This is actually the wolfHSM. This is our release 0.7 that's set up for the Tricore 375. The Tricore 375 is a 3-core device. And this time we're going to execute our standard wolfHSM server initialization on the HSM core. It's been set to boot first, then it releases core 0, which invokes a standard client initialization and then connect. We then walk through our client echo test, which is literally the same test we run as a unit test. In fact, I'll pull that up in a second. We run an NVM test, same exact test code to perform reads and writes to the HSM memory. Again, these are all triggered from the client. The server is simply sitting and waiting to get specific requests that come in. We do a random number generation test, and then in this case, we're going to show walking through importing an RSA key, committing it to memory, exporting it, erasing it, and then asking it to generate a key from that. These are all client-driven calls using our standard HSM client APIs. And at the end of the test, we trigger 2 different custom calls. These are calls that are not in our HSM library, but were in the HSM application build that we had that extended as custom HSM callbacks to disable Ethernet and then likewise disable the debug interfaces. These, again, just are triggering features that are custom to the Tricore. Logically, this looks similar, except in this case, we're going to hold both core 1 and core 2 off as we run this test, just as a choice. And let me switch back over and get that back up again. So that was again, this is just serially connected, and the output comes through the exact same mechanics. So let me hit this. Oof, went really fast. So let me scroll back up and I'll walk through some of these pieces and I will show you how the same test looks at from a host. So I'm going to click this over here for a second. So this is on my Mac. When you download the wolfHSM source code in the test directory, there is a unit test that we run. I'm simply going to kind of run this test and I'll point out how the exact same tests we run on our host system are present in our embedded systems as well. Again, this is the point of going to something that is portable so that we can continually test and verify how these things are executing. Sorry, let me scroll back up to get to the right section here. All right, so this was, oh, I apologize. I think I went too far. Yes, I did. So let me start at the beginning. So when the Tricore fires up, it's telling us where its communication buffers are. Again, this is just for debug perspective there. We've allocated 4K total for our communication buffers. That's 2K for a request, 2K for a response buffers. We did allocate a second print buffer. This is how we're getting the output from the HSM server to be able to be seen. This time when we initialized the HSM, this is not using a custom call. This is using our HSM client connect function. We requested from the HSM to say, tell us status. We got that. Now we have closed loop communication with that. As we come down, we're going to jump right into our first one. The first is a host client test where we're simply issuing a request to be echoed back to us. This is a text message, and then we get the answer that comes back to show that we've got closed loop communication. That same test is, oh, I apologize. There it is. So this is the same test with additional debug, but you can see we're doing our send and response requests, and we're getting those exact same answers back as what we expected. Same exact test setup. We simply linked it and brought it in there. The next set of tests are NVM tests where we insert objects. And you'll see those in our unit test as well. The last set of tests, let me scroll down to show you what those, again, I just ran this live, so it is what it is. The last piece of test is where we generate a sequence of random number generation tests, and we're not dumping any debug output on there, but it's going through generating the random numbers and verifying the numbers look good. They're not fixed and they're not stuck. We then perform cache and exports. We evict a key. We then pull that back to make sure we can find it. We erase that key, then generate an RSA keygen. So this exact same test when run on, again, I apologize, I built this with a lot of extra debug. When we run that on the host, I do apologize for scrolling. There's, you can see the exact same tests are running on the host that we expected. In fact, on this one, I had ECDH and ECC compiled in our test setup. So it saw that they were there, and then it ran from there. You can see a couple extra steps were done on the host as well that shows additional multi-session support to handle that. In this case, it was only a single session, so we didn't run those tests. And at the end of the day, we finished that off. The last piece was adding in these custom callbacks, which then trigger these to execute and then go back from there. So from that perspective, we've got the Wolf Crypt bottom end tests that can execute in our portable. We've got wolfHSM upper level tests that once you've got your bottom end port done, you can execute these functions. You can develop in the POSIX simulator with wolfHSM, and then simply recompile, swapping out the bottom end configurations to whatever the port that you're on. This also gives you some flexibility. If you code it up, let's say for a Tricore TC3 and you want to move to, say, a TC4, the rest of your crypto code doesn't necessarily have to change. And that was really kind of the point of why we wanted to have some flexibility on the back end there. So let me switch back to our guy here, and I'll finish off this presentation and then jump into questions. So I'll just kind of walking through some of these different pieces as I walk through that. So where are we going with this wolfHSM? So our next set of ports that we're working on after we release these is the Renesas RH850. I think that's already in start. And so we'll be fully supporting the HSM and the secure elements that are on that chip. We're going to do another example using a TPM as the backing store for our wolfHSM. So this allows you to have the rest of the features of wolfHSM, but instead of actually being on an HSM chip, you're going to be using a TPM as a backend. That's a model we've had a couple of customers approach us about, but this allows you to write the code once, and you can use this as the backend. And then likewise, the TC4, we just got that in-house, and we're going to be starting the updates to handle the TC4 as well. Currently, we have PKCS11 in a beta sense coded up, but we haven't released it. So we're going to finish off our PKCS11 full provider. We'll be offering some features to provide secured client-server communications over buses that can't be trusted, or let's say you're over a network protocol instead. And we are actively working our AUTOSAR crypto driver. We're working that on wolfCrypt as well. But this would allow you to use either wolfCrypt as a pure crypto driver or wolfHSM as a pure crypto driver. We also have some additional access controls that are coming online that allow you to have multi-sessions and ensure that sessions can't get into each other, and that data written by one session can't be read or can be read by a different session, and as well as multi-session examples where we light up all the cores and pound the HSM, from that direction. So those will be some additional examples that are coming up. From a links perspective, you can have access to the PDF version of this, which has these links active. The wolfHSM product page, you'll see our GitHub repos, which are public. We do have private repos that are holding the NDA protected ports that we've got for both the Infineon and ST. And then once you engage with us, we'll make sure that everyone's got NDAs in place, and we can release snapshots of that repo to you as well. wolfCrypt, wolfboot, and wolfPKCS GitHub repos are all there as well. All right, so that was the end of the presentation. Let's see if we can jump into some questions, and maybe I can answer them for you. Cameron, if you're ready.
Yeah, awesome. Hey, thank you, Bill. That was extremely informative. I know I learned quite a bit there. I got one question here starting us off. How is wolfHSM different than hardware vendor provided firmware solutions?
Well, I think I mentioned this early on, but I do want to go back and point out that when we consider what we're running on the HSM core, this test application you build yourself. So this allows you to put any functions in here that you need, get rid of the functions that you don't want, and then extend it. So those custom callbacks that I mentioned, This could be a token generation that happens to be custom. It could be an API that reaches out to some other hardware. It's anything that needs to be done in the secure context. Is typically, it's not a one size fits all with the commercial products that are currently out there that are trying to give you a pre-built binary that's been certified. This instead puts you in the driver's seat as a customer to place what other code you want to have in there into the server context and execute. This gives you that crypto agility that we're talking about, can give you some diversity if you needed to have more than one implementation of a certain API put together. It gives you lots of options. It puts the customer back in the driver's seat to leverage this cool technology that HSMs are without necessarily tying your hands in terms of how things are working.
Awesome, thank you. Next here, what is the licensing model and the source of libraries provided, or source or libraries provided?
Great question. So the licensing model, again, with all of our wolfSSL products, we try to work very closely with our customers to come up with the right licensing model, whether it be a lifetime usage for a specific product line, or whether it's a per unit type of license that you would go with. I would definitely reach out to our business reps to get the options that are available to work with it. From a release perspective, our public POSIX ports in the base HSM library are available as LGPL v3 open source code, which also allows it. Everything we do is dual licensed here at wolfSSL. So if you need a commercial license, we can provide that as well. But everything is GPL v3, not LGPL v3. It's GPL v3. Which allows you to use the code as you see fit, and then kind of move from there. The private repo holds the port specific that are covered typically under NDA with some of our vendors. I'll give an example on Infineon, since we did the Tricore stuff today. Infineon has said, hey, if a customer either has an NDA with wolfSSL, or if the customer has an NDA with Infineon, then we can release the source code for that port to that customer. So that would work through some of the intellectual property issues with some of these vendors who want to protect some of their internals of how these things actually operate. But from a licensing perspective, everything we do is GPL v3 to make it easy for our customers to get in there, try it out, kick the tires, and then modify it however they see fit.
Awesome, thank you. Next here, can wolfSSL TLS 1.3 leverage wolfHSM for private key and encryption methods?
Absolutely. So because we coded up wolfHSM to be a standard crypto callback, and this is the client. Let me show you. Sure, yeah. You can set up, when you create your SSL context, you can point it to use this wolfHSM dev ID once you've set up your client to do that. From that point forward, that SSL context will attempt to pass all requests down through the crypto callback layer to gain access to what the HSM has got. Now, because if you're talking private keys, there might be an additional call that you'll have to add to give it a hint of which client key identifier that you've got if you don't have the key material available. So if let's say you have just the public key that you're using to verify, but you don't have the private key, you'd have to add another function call in there to trigger that to do that. We are looking at a tighter integration that would allow you to not only set the context, but then also associate in the key store that the SSL, the wolfSSL has. It would be able to line up those certificates with the pre-known keys that are already there. But at the end of the day, currently, yes, it can all happen. Currently, you do need an extra function call to associate a private key ID with a specific context, but we are looking at streamlining that. Functionally, it is 100% and expected as a use case.
Awesome, thank you. Next year, do you need to write your own server application, or is there a standard one that works out for the box with most functionality for your supported ports?
Yes, we do provide a kind of a base server that you can build and put together that has a minimal image manager. It's configured to be able to run our unit tests that you've got configured, and it should work out of the box. Definitely recommend to go back and reconfigure that to meet your requirements, though. That's the joy of having this all being open source and configurable. You can tailor it down to be exactly what you want. The choices we've made, let's say, maximum RSA key sizes, I think we picked 2048. You may want to do a larger and stronger key. So yes, we can give you something that can work out of the box. In fact, the example I ran today that is the built version that we delivered, which has a certain configuration in there. That is exactly what we delivered with the source code. But yes, it's enough to get started. It'll answer any request that you give it that it's configured to do. But as we move forward, definitely want to make sure that you have your own. The source we give you is definitely enough to start with. Easy for you to tweak.
Awesome, thank you. Next here, if we are currently using another HSM solution, how difficult would it be to migrate to wolfHSM? Are there any tools or resources available to assist with this process?
That's a very great question. So it's very hardware specific. I can tell you when we release our Tricore build, we provided an extra video on how to configure the chip to enable the HSM, because some of these chips are very, I don't want to use the word fragile in a sense that they're not sturdy, but they're designed to be cryptographically fragile, that if anything goes wrong, it bricks the chip. So there's definitely a sequence that you have to follow to enable the HSM to make sure it's correct. Now, if you've already got a device that's been configured for another vendor's HSM solution, you might need to walk through how to undo that configuration first, if it's even possible, to be able to place our code in there to be able to be used. From a code perspective, if you're writing at either the AUTOSAR crypto driver layer or as a direct SHE user, those function calls are simple mappings to the corresponding function calls inside wolfcrypt. You'll have the same limitations, let's say for SHE perspective, you've only got a handful of keys that you can use to do that, but your code wouldn't necessarily logically have to change that much. You definitely have to change the spelling of your APIs to either wrap our function calls or to use our function calls directly. The other advantage of you going with the wolfHSM solution is that these protocols can be turned on and run at the exact same time. So you can mix PKCS11 calls, direct wolfHSM calls, and SHE calls, either from different nodes at the same time or from the same node at the same time. They're designed to work with each other. So there'll be functions that are available to you that maybe were not available to you from a SHE interface that you may want to take advantage of. So is it hard to do? It's really a function of what platform you're on and who you're currently using. If you have a bare development kit, we can get you running on that development kit, from scratch pretty quickly. In terms of the resources, we will continue to add more and more, videos, walkthroughs, and readmes as we get more platforms on there. But at any moment, you can always reach out to support@wolfSSL.com. That goes directly to our trouble ticketing system, and our engineers are the ones who service that. We don't have a separate service group. The same guys who are writing the code are answering the support calls, and you can always reach out and ask questions for that, whether they're HSM related or if they're wolfSSL related. That's your best bet. We're here to help you succeed, and we'd love to help you to transition to whatever you are working from.
Awesome. Thank you, Bill. A couple more here. What are all the alternate security solutions instead of using HSM?
In terms of the grand scheme, we picked on three at the very beginning, which was like a trust zone solution or virtualization, where this is ARM specific for trust zone, where you can have a hypervisor in essence that stays in memory, executes in a slightly different address space, and then services function calls from that perspective. PSA, the platform security architecture from ARM, lines up with that. And so that would be one way of doing it. It has its drawbacks in our opinion because it doesn't leverage hardware as fully as it can. The trust zone does provide some address space protections, and from a hypervisor you kind of get the virtualization, but it doesn't give you the same level of solution that you want. TPM is kind of the other direction. Again, that's an alternate solution in our opinion, but it's not tightly coupled or user programmable. HSMs and really what they used to be called secure elements really kind of are in that same boat. The only other model I would recommend to take a look at there are some secure elements that don't have the ability to have a separate core. So when we consider an HSM core, we think there's an execution context. I can compile and run a program on this HSM core. There are other models where you have application cores that simply have access to, let's say, a set of registers that do cryptographic operations for you. So it's not I'm going to request this piece to do the work for me, and then I'm going to wait to get the answer back. This is go do this crypto algorithm, I'll feed you data until you're done with that. So from a secure element perspective, you'll find there's a third model that's out there that is an HSM, but without a separate core. In fact, the Renaissance devices, they have the same exact core or same exact secure element, one with a core that's attached to it and one without a core. So that would be kind of a hybrid approach that would kind of fit in there. Aside from this, there are a lot of custom chip-based solutions that maybe can lock flash or can modify a ROM-based boot up sequence to kind of do a pre-boot execution type of solution. Those are all in the realm of security elements. I think HSM is kind of the full featured, and really from an automotive perspective, it's kind of coming into its heyday at this point because of the increased cyber requirements. It's difficult to bring a pure TPM solution through, or a pure virtualization perspective through, or a secure element solution through, because they only solve parts of the problem. From an HSM perspective, I think it puts you in the driver's seat to be able to solve the entire crypto stack and cybersecurity requirements in a separable component, which in my opinion is probably the ideal solution to consider. But in terms of the overall universe, there's plenty of options. If there's crypto hardware out there, we've probably ported it to it. So you'll see things like CAM drivers and other things in our wolfCrypt library that can attack parts of those problems. But wolfHSM is our first attempt to bring those together and solve key management as well as non-volatile storage, in addition to crypto, all at once, and put it into an interface has more features than PKCS11, doesn't get the same limitations as a SHI or a crypto driver from AUTOSAR, and then really make sure that we can be portable to the next generation of hardware that comes out, because we started off with a fairly generic model to begin with. It meant to be a technical answer. I apologize. It sounded like a sales pitch at the end of the day, but there was a reason we went down this road. From a model perspective, we think it's likely the model that's going to have the most legs on it.
Awesome. Thank you, Bill. I got one more here. What are the unexpected challenges to implementing an HSM based product?
Bricking the board. I can tell you that if you've ever done any work with some of these secure components, if you haven't broken 2 or 3 of them, you haven't done the work yet. I can be honest. Unexpectedly challenging build environments as well. So if you read these from the Infineons and the STs and the Renaissance, it sounds like this stuff is just ready to go. It's production grade, pull the trigger and you're good to go. But even the development environments are broken to do this. The documentation's surprisingly not accurate, and it's a big challenge. So we found our ability to do this is a hedge against future support calls. We said, let's just get into these components, become experts in them, so that when we get people who are asking these hard support questions for how difficult some of this stuff is, we've got the experience, and now we'll have a library that you guys can start with that solves a lot of those hard problems. It might make decisions that you don't agree with, but at least we will document it. Hey, we chose to put the communication buffers in this area and use the uncached window feature to ensure concurrency control. We've made choices that may not be right for you, but at least we've made the choices and can give you a functional component that doesn't have you starting off bricking your chip. But so from an unexpected challenge perspective, permanently damaging hardware happens far more times than I'd like to admit. We'd like to stop our customers from doing that by letting us damage a hardware first, tell you what not to do, and then give you a path forward. Build environments, again, very challenging. Sometimes you're stuck using Windows and certain IDEs that you may not like, or compiler sets that you're not happy with. And so we focus strictly on getting the GCCs and the freely available environments to do these builds for us. And then likewise, documentation. Many of these secure sides have documentation that's not been fully fleshed out. And so as we go in there and start, poking these things, we find on a regular basis areas where the documentation is simply wrong. And it's definitely a challenge. From a risk management perspective, you know, these are our products that have a lot of years on the silicon, but I still feel like the build environments and documentation are still behind in terms of where the publicly available commercially available side on the application side is. It's the stuff is not easy, and it's very frustrating sometimes to get answers out of the vendors that really get you to move on. So there's my 3 items of complaint.
Awesome. Thank you, Bill, for hosting this informative webinar, and thank you everybody for taking the time to join us. I will be emailing out a copy of the webinar recording and PDF slides. Again, you can keep up with us for our upcoming events, to meet our team in person. You can read our blog posts and get the latest on wolfSSL updates by following us on X, connecting with us on LinkedIn, or subscribing to our YouTube channel. If you have any additional questions, don't hesitate to shoot us an email over to facts@wolfSSL.com. We're here to help, and thanks again. We'll look forward to seeing you next week on June 6th for Wolf Engine versus Wolf Provider, discovering solutions for OpenSSL compatibility with software developer Anthony Hu. Awesome. We'll see you next week. Bye-bye. Oh, actually, it looks like we did have one more question come in. I'm gonna answer that. It came in at the last minute here. What about ISO 26262 certification status?
Excellent questions. Those things like ASIL-D as well. We deliver source code to you, and then we help you get through the certification. Our wolfCrypt library has been through the safety critical certs with our customers many times before, and so we've been instrumental in helping them explain, you know, either get waivers or walk through, you know, code reviews to explain why what we're doing is either in the safe mode and can be approved again. So because we deliver the source code to you, you know, we're going to let your systems and your quality systems control that, and then you can tailor that down to match that. We're there to support you to get through the certification. So we don't expect we're going to get our code independently certified that in such a way that you'd be able to use that right out of the box, especially since you're going to recompile and configure it anyway. So we're there to support that, but independently, we're likely not going to get these independently certified. The processes we have internally for software development and test, you know, we're pretty explicit about how we do that. We do meet all of the intents of the controls that are asked for in those ISO specs. But again, we're not going after independent certification. We're there to help you get your stuff certified as a partner in that. Great question.
Cool. Yeah, glad that came in. Alrighty, folks. We'll see you next week. Take care.